Okay. That works. Let's see. Still hearing that this. Oh, it's coming from this guy. Okay. Okay. Thank you for joining us today. This will be our last Altera sponsored live stream for 2024. If you're joining us as we start, thank you. I hope this will be a fun one. I wanted to go through all the steps to try to use, I guess, the closest thing to a state-of-the-art neural network inside the Agilex 7, and kind of just learning the steps myself. And I hope to be able to kind of share what those steps are. So today we're going to be looking at Altera's FPGA AI suite, and they're using with the OpenVINO tools. And we're going to take the YOLOv8 classifier neural network, and using the ONNX export feature, be able to bring that onto the Agilex 7 FPGA. And I'm FPGA Zealot, or Andrew Wilson. Thank you for joining the stream, and this is an Altera sponsored stream. And if you want to follow me, like, or whatever, you can find me on YouTube, Twitch, X, Twitter, LinkedIn, whatnot. So, disclaimers: yes, this is a sponsored live stream. I am not employed by Altera. I do not offer official support for the Agilex 7, FPGA AI tools, or OpenVINO, or anything like that. This content channel is created for information purposes only, and all the opinions are my own. So these are kind of the three major steps we're going to go through today. YOLOv8, what it is, and why it's of interest. What is, I guess, how we're going to use the ONNX open standard to be able to export, manipulate, and optimize the YOLOv8 model for the FPGA AI tools, and how we go about verifying that it's working correctly and be able to kind of benchmark that on the FPGA. So thank you for joining us. If you want to say hi in the chat, tell us why you're here, where you're from, what your interest in FPGAs or AI is. Hopefully this can give you a good example, I would say a competitive example of AI and an FPGA with the Agilex 7 versus a GPU or a CPU or something like that. Even looking at the TPUs on Google Colab. If this is your first time joining in one of these Agilex Altera live streams, we're going to go a quick overview of what we've done so far with these different streams. So the first thing here. So first thing first, Altera is a company that recently branched off of Intel's Programmable Solutions Group. They're known historically for their FPGAs, ranging from the Max, Cyclone, Aria, and Stratix. The most recent family is the Agilex. You can find a lot of academic boards, you can find a lot of hobby boards. There's a lot of, I would say, retro gaming boards that use the Cyclone FPGA as well. Today we're going to be looking at Agilex 7, which is kind of like the middle of the pack, upper end of the pack for their Agilex family. So we're going to look at Agilex 7 FPGA, which is but to not as intense as the Agilex 9. Agilex 9s are pretty high-end FPGAs. And we're going to be looking at, they have, I think we just have the F series. Yeah, we have the F series. I'm trying to see where the dev boards are so I can show you which board we have. I guess I just click the F series, and then we should have development boards. That's what I want. We want Agilex 7. We're going to look at the SoC development kit. This one? That's something right now. No, it's a different SKU. Over here, this is the one. Okay. So this is the board we'll be working on. It's Agilex 7 SoC development kit with the 4 F tiles. We can go and look at it real quick. There we go. Camera focusing better. Okay. So we currently have 2 sticks of DDR. This is kind of required for the FPGA AI system. And then we have the little solder card on the top, which is kind of your processor expansion board. And that's mostly, and then we have the flash memory over there on the bottom right that we're mostly using for the boot up, the U-boot and the FPGA image that's loaded on power up. So that's the board we're using. And if you go look at my LinkedIn account, my YouTube account, Twitch, whatever, you'll find that we've done some various videos. We brought up the Agilex 7 FPGA. We've done some basic video accelerators, and then we've done a few examples of the FPGA AI tools, looking at the pre-built examples. How do we use Python to accelerate prototyping with it, using YOLOv8 and bounding boxes to detect traffic, and then doing a PyTorch neural network from scratch using the MIMNIS dataset. Just a very basic example showing how we can push through the whole flow with this. So now for this final stream, we're going to look at YOLOv8. And YOLOv8 is a much more competitive system. There's one more link I wanted to go back and look at real quick. If you have questions about the flow of how this FPGA AI tool works, go ahead and look at the design guided journey, and it talks about each of the different steps in using the FPGA AI tools. And this is really useful for starting with what you understand and branching out. That should be good for the background information today. So we're going to be looking at Ultralytics' YOLOv8. So YOLOv8 is a rather, I guess, cutting-edge classifier. It's rather new. It's not like an old YOLOv2, V3, or V5. This is a rather new detection suite. There's different variations to the model. You have detection, which does bounding boxes. Segmentation, which will break down an image into different categories. Pose, which will give you your human pose and whatnot. Orientation of objects and classification. Due to the kind of not the restrictions, but the detection, the bounding boxes for YOLOv8 have dynamic sizes, and you need to figure out how to fix those bounding box sizes when you want to port it over to the FPGA AI system. And I hope there should be a good example, hopefully, in the future about that, but we're going to go a little bit basic and do just the classification, ignoring the bounding boxes and just classifying whatever the whole image contains. And we're specifically going to look at the smallest one. Right here, which only has 2.7 million parameters. I should really look at what limitation we can support on this board, and maybe we can do that today if we have extra time. Look at building the bigger systems and see what happens. Maybe we can do that. That might be a good breakpoint to build up. So we'll do that. We'll run the n size one on the FPGA, and then we'll move up to a bigger size and see how the system handles it. And the really cool thing about Ultralytics, it's really easy to port in and test your model. So what we're going to do right now is we're going to pull up the model in a Google Colab. And Google Colab lets you utilize a smaller TPU, so we can see what the performance with something that's a little bit more optimized in the CPU. Okay, so we're going to connect. And we're going to go through the steps for the YOLOv8 model, classification model. And while we're going through this, feel free to ask questions, comments, or whatever. But we have plenty of time to have a discussion about what's happening on screen, or any other questions you have about Altera, FPGAs, or their tool suite. So we're going to be using the CUDA capable TPU and run our YOLO model. Is there an echo? Oh. Thank you. Echo gone. Thanks. Echo gone. Okay, sorry about that. The audio should be fixed. I have to keep an eye on that next time. Okay, so here's an example where we take the Ultralytics YOLOv8 model. We're able to send in the bus image. Put that real quick. But yeah, it's a bus image. And then we can predict it as a minibus, a police van, a trolley bus, and get, what classifications and confidence that are out of it. So next we can export this model, which is where it will get interesting. Okay. So we now have our ONNX model. We're going to go ahead and download that. Okay, let's go find a good spot real quick. Models, new folder. Okay, so a really cool thing about the ONNX model is we can view it with this app or this website. Going back to here, we can view the entire structure of the neural network. Okay, so we're going to pull up the FPGA tools in the Windows subsystem Linux. So To do this, we're gonna get our tools. I have a weird location for them. Your location, fine. You'll want to know where you've installed your tools to be able to do this. Okay. So now we're going to go to where we save them. Okay, cool. And we have it there. Back in our collab page, we have the way to optimize it, which is using the model optimizer from OpenVINO. And this will create the XML file that we then can use the FPGA AI suite to convert to a platform, a binary for the FPGA. So we're just going to run this command. You can find this Google Colab on the GitHub in the description. Okay, while that's running, we'll take a quick break. So if you're joining us, if you're new to the stream, we are building, go back to description. We are implementing YOLOv8 onto the Agilex 7 using Altera's FPGA AI suite. This is a sponsored stream. I am FPGA Zealot. I'm glad you could join us. And if you're new, feel free to chat in LinkedIn, Twitch, or YouTube, and I'll try to keep up with questions or comments. I'm glad that people noticed that the audio was echoing and we're able to address that. It should be clear now. If you do have any audio issues later in the stream, feel free to say something in the chat. Okay. So when we compile the ONNX system for the FPGA, we're able to get the expected performance. And this is expecting, not expecting, but hopeful that you could get up to 500 megahertz. Our system's running at 200 megahertz with the example design, but if you want to push the timing on your FPGA, you could get better performance. And this is actually pretty good performance for the YOLOv8. We're able to get 2.7 frames per megahertz. So at 200, we should be getting close to 550 frames per second on the FPGA. And with this example, the FPGA, the architecture here, right? The example architecture, this performance arch is only using about 10% of the Agilex 7 FPGA. So we have a lot more FPGA we could use if we wanted to introduce other logic. And potentially some more operating cores for the FPGA AI core that's in the FPGA. The only issue is being constrained by the DDR memory, which is going to be dependent on your system, how many constraints you use, and whatnot. So before we run this on the FPGA, let's compare this to the TPU that is running on the Google Colab page. So this is just going to generate 2,000 dummy images and run them through the TPU. And we'll get an average of 700. You can run this a few times and get a little better. It maybe up to like 1,300 and stuff like that. And it kind of depends on what the GPU is doing. The FPGA, on the other hand, is very deterministic in how much processing it takes to do each image. So let's go ahead and run this on the FPGA. I may actually have to reboot the FPGA, but that's okay. And then we can maybe try some different variations. Okay, the FPGA is going to be over here. We're going to go ahead and we'll look at this later. But we'll reboot for now. And let me bring over the Paraterm window so you can see it boot up. We are using... So we have a question in Twitch from Keratin of what size primitives, I guess, what size binary we're using. And when you use an FPGA, you could potentially look at fixed point, floating point, or integer. And in reality, integer and float and fixed point are probably going to be the same. We are operating under that we can do 32-bit floating point. So our performance, we're not doing any quantization on the neural network. So we should be able to get the same performance if we have the identical input. But you'll see later that the pre-processing stage in the FPGA is a little bit different than what the YOLO is expecting. So the performance, the accuracy varies a little bit. And if I understood exactly what pre-processing is required, we should expect to get to about the same accuracy without any quantization effects. Okay. We'll log back into the FPGA. I'll go ahead and run the benchmark. So here we're running on the FPGA. At 200 megahertz, we're able to get 577 frames per second. If we were running it at higher 500 megahertz, we would be able to get the 1300 and the 2.7 frames per megahertz. And this lines up a lot with what we are kind of seeing on this TPU right here. This TPU, let's see if we can look at the power. So the power, we could look up here, right? It says 10 watts. I wonder if we have any updated power. 28 watts. So let's say the TPU is minimum 30 watts when operating. The FPGA, let's pull over this right here. The FPGA is operating about, we'll say 12 watts, maybe a little bit more, 13, 14 watts total for operation. So the FPGA is definitely a lot less with similar performance to this TPU at the moment. But let's go back here, and while we have a moment, let's load some bigger YOLOv8 models and see how the performance or the frames per second, how it affects the frames per second of the system. So we'll just do the S next. And we'll just export that. And what's it? M is next? Yeah, M is next. We'll do probably S and the M, and I don't think we'll be able to go much bigger than that. Okay, so we're going to take the S, download it, put it into the same folder, take the M, download it, put it in the same folder. Let's go back to here. So we're going to S. So we got a question in chat. I need to go up one. We have a question in chat about a tutorial to install the FPGA AI tools. So I am using a Docker image. There are tutorials and instructions about how to load the Docker image, whether you're doing that on Linux or on a Windows subsystem Linux. But the the Docker image, it makes it a lot easier. And if you look at my first FPGA AI tool, I should go through how the Docker image works. Okay, so let's go into the YOLOv8s and let's go back here to DLA compiler. Where's the cursor? Weird. Okay. Oh, we don't. We'll just do. Yeah, it saves in the directory. That works great. Sorry. Okay. So we were able to get 2.7 frames per megahertz with the nano model, the N model. Now we'll see what the small model gives us. It being in one subgraph is important. If we go above one subgraph, I need to learn more about how the FPGA tool works in that situation. Okay, so we went from 2.7 to 1.5. Interesting. Maybe we'll see how the TPU handles that. So next, let's try the M1. So while that builds, let's talk about the parameter increase. So we lost about, I don't know, a frame per second, so maybe about 1/3 the performance, but we got 3x more parameters. That medium is much bigger. We're jumping up to 17, so it's another like 3x difference. Still one FPGA subgraph, which is good. Oh, okay, so that went down to 0.5, so we went from 1.5 to 0.5, so it's about 3x difference. So that's basically linear with the number of parameters you have to use. So basically our entire design is dependent on the DDR bandwidth. As we increase more parameters, we require more DDR bandwidth. So more DDR banks, faster DDR would help improve the performance of this system. Okay. Let's go ahead and rerun this with the M model. It was not happy. Oh, we ran out of space. We could not run the M model. Is there a way we could clear it? We used up most of the GPU memory. It's only 15, and we would need 17. Okay, so we can't even run this on the TPU at the moment. We don't have enough memory. Okay, that's fine. Going back to our little presentation here, we're going to move on to how do we modify the ONNX model to help with our DMA input. So this is kind of important for the YOLOv8. It's kind of hard to search for, but the YOLOv8 is expecting an input between 0 and 1. And we need to either do this pre-processing with Python, or we need to add the scalar value to that first convolution right here. So this is expecting a 0 to 1 value, but our BMP files, our image files are 0 to 255. And we can either do pre-processing in Python on the slow ARM processor, or we can do pre-processing with this convolution, or with another convolution of sorts, a scalar convolution as our first step. So we're going to go through and modify that. Want to open. Okay, let's go ahead. Okay, this is doing the weird USL. So we're going to go do a new window. And we're going to just open this, will be fine. Go to our stream one. Go look at our graph. Where's our preview? I have this installed. Did it refresh? Okay. Sure. That one's installed. Guess we'll try again. Okay, this one is the one I want. Okay, so this is expecting 0 to 1 and the float 32. But we want to change this so it applies a scalar to the design. So there's two ways we can do this. The first way is we can actively modify the model. So let's go ahead and load the end model back up. And what we can do here is we can create a scalar. In all honesty, I use ChatGPT to help me a lot with this. I find ChatGPT to be really helpful with doing some quick Python changes and whatnot. But this is basically making a constant value node inside the ONNX graph and creating a scalar divider and using the input of the graph and the constant 255 and creating a normalized output of the 0 to 1 values. So we can easily apply this to the 8N, the nano model here. And we're going to have a divide by 255. I'm going to go ahead and download that here. While we can go up here, go back to this, and we can target what's it called? A model. Here we go. If you joined our stream in the past 15 minutes, welcome. I'm glad you could join us. This is a Altered sponsored stream. We are looking at taking Ultralytics's YOLOv8 classifier and implementing it on the Agilex 7 FPGA. I am FPGA Zealot. You can find me on YouTube, Twitch, and LinkedIn as Andrew Wilson. Feel free to have any comments or questions in the chat. We're going to continue by looking at how to add a scalar for your images into the ONNX model or with the OpenVINO compiler. Okay. So we've done that. What we could use, let's look at it through here. So if we open the new ONNX model, right? We now have a divider right here, and we can look at the B value, which is just 255. So we're going to take the image divided by 255 to normalize it between 0 and 1. Works great. So then we've optimized or did the model optimizer with OpenVINO. And what did we call it? Divide. So in here, we can then compile it for go ahead and compile it for the FPGA. And you'll see that the performance is identical. We didn't add any nodes. It just folded in the scalar into the first convolution. So we have the same 2.7 performance. Actually, let's scroll up to make sure it's not. Oh, did it clear it? Well, so that's our performance. And now if we go look at the node graph there, and we open up the divide one here, the graph, and then we can compare the two. So we have the old one here and the new one here. So we basically added a scalar. So we've gone from 2.68 to 0.0105, right? So we've added the 255 divider into the first convolution, which allows the FPGA to take in unaltered the 255 bits for the image. And there's actually a lot easier way of doing this with the model optimizer. So we go back up here, go back to our original command for the nano. Right here. And all we need to do is set scale 255. And then we can go into the YOLOv8 and then compile that with the DLA compiler. And then we'll look at that dot graph as well. Hopefully it should be the 2.7, like same frames per megahertz. So your model accuracy. So we have a question from the YouTube chat asking about model accuracy. How do you view your model accuracy in the FPGA AI tool? So your accuracy should be identical. We're using floating point 32, which should match the normal operation of your system. So if you have the same input for both systems, you should have the same accuracy. We'll see that the accuracy changes a little bit because the pre-processing may be different. It'd be fun to dig into what pre-processing is optimal for the YOLOv8. It's a little hard to chase that down. I probably have to look into more of their code of how they're processing the image correctly. But with this flow right now, I don't have any test data set, validation data set to measure the accuracy within the FPGA AI suite. You can measure the accuracy in your normal PyTorch, TensorFlow tools. You should be able to measure the accuracy there. When you do quantization, you'll want to rerun your validation. We are not doing quantization in this example. Okay. So then we'll go look at the node for that one. So that's going to be the S right here. Just a quick comment on the accuracy that we were talking about. The accuracy is dependent upon your parameter values. And if you run the FPGA or if you run the network on a GPU, and if you run on the FPGA, your convolutional coefficients or parameters and your operations should be identical. So there shouldn't be any difference in your math between a GPU implementation and the FPGA implementation. Unless you're doing some optimization specific for GPU or some optimization specific for the FPGA that would alter the accuracy. Okay, so yeah, using the model optimizer, we are also able to get it into the correct shape. Okay. So we now have a binary file. Right. This file right here, the YOLOv8 bench, is what we use for a benchmark, and we can also create a version for the DMA operations, which is basically you add the no folding option. See if I can history grep delay Okay, yep, so many. So if you do the folding option right here, a little bit, the folding option equals 0, we then can use it for our DMA example that we're about to run. Okay. So now that we have a model, we can use it on the FPGA. So to talk about that, we're going to look at the files that run the inference and run the image DMA. So for this example, I did change the inference example, so you can find this on the GitHub. There's a lot here, and we've talked about it before, but basically what happens is right here, we collect the output of our inference, and we open up a shared file between C++ and Python, and we're basically just going to copy and paste one by one the output values into the shared memory so that Python can use it. And then we added some additional semaphores this time that allow us to measure the timing with a lot more accuracy. Still, C++ and Python overhead, but better accuracy of how long it actually takes to do the inference. Okay, so let's run this example using our YOLOv8 local. If you watch the previous videos, these are values that are used for like red shift, blue shift, or green shift for this one. Green shift and blue shift. We set those for 0 for now because I don't know what the correct blue, red, green shift would be for this example. But this basically grabs a bunch of BMP files, or in this situation actually JPEGs, and does a letterbox effect on them and sends them to the system. And then when we get it back, we compare. So we send the images over the DMA, and then we measure the execution time and figure out the top 5 classes that are being used. So running this will be a lot better to show. And we can maybe look at some of the pictures that we have running. So this should be easy to just run the inference stream. We're also going to see if we can drop this example in here real quick. Okay, I guess we'll open this in File Explorer and drop it. Okay. CD app, and then Python 3, YOLOv8, local. And these local images, are they in the test? So we should print the names. So we should see. Okay, let's see. The DMA engine's ready. So let's go ahead and do 2 terminals. Agilex. Okay, cool. Okay, cool. We just ran through the images, and I think we printed the name of it. Okay. Well, the obelisk, a trench, which is a fish. This is an ox cart, and it's only the 3rd one. It's not the top one. We have the goldfish, toilet paper, and the minibus. And you can see the accuracy is a little bit different from this bus example than what we saw on the TPU. And that's because we are pre-processing the image differently. And that's the accuracy is going to vary. Because the neural network is expecting a certain type of formatted picture to meet the accuracy that it was trained on. Okay. that real quick. Be a little bit better. Go ahead and bring back the board in the corner. Upside down. Okay. So, if you have any questions so far, we're about to do a little bit more performance testing going forward. And comparing the power consumption, the timings. Like the execution time for this is about 3 milliseconds for the inference time, and that the DMA portion takes quite a bit. Maybe it's more water later. Okay, I'm gonna go ahead and reboot the FPGA. The DMA core gets a little upset if I start playing back and forth with some of these things. Okay, and this is what we're gonna look at next. Okay. So the next step is that we're going to run the YOLOv8 locally on my tower on a CPU, and we're going to run it on the FPGA. We're going to look at accuracy, time, and power, potentially. Oh, I'm trying to remember a good way to look at the power. I don't know, my system kind of uses a lot of power, so it's a little hard to estimate exactly what the difference is for running it. Okay. Okay, so if you joined us in the last 15 minutes, thank you for joining us. This is a sponsored Altera stream. We're looking at the FPGA AI suite in OpenVINO, and we're going to be using a YOLOv8 classifier network, and we have gone through the steps to export it as an ONNX model and to implement it on the FPGA. Right now, we're going to look at more of a live demo, looking at accuracy, timing, and power. A little bit better, comparing my local tower, which is like an average gaming computer, right? Nothing terribly impressive about it, towards the Agilix 7. And it's important to remember that the Agilix 7 AI core is only running about 10% of the FPGA. So there's still a lot of fabric that could be utilized for post processing. If we were able to utilize more DDR channels or faster DDR, we could improve the performance of the AI as well. Okay, so if you have a Python notebook, you can run these commands, hopefully, and be able to run the YOLOv8 network locally. So we're going to go ahead and clear all the outputs. We're going to restart and just kind of walk through the steps of what's happening here. It's running. Okay, so after we install Ultralix, I can show you that we are not running any no CUDA cores available for this. I do have a GPU. I did not get it set up correctly in time for this. And we can do a quick benchmark and show the lackluster performance of running just a CPU. It was able to, I mean, it's still pretty good, right? We still are able to do 200 images a second. That's like, against the 500 running on the FPGA, it's not bad. You'll see that the inference time is still slower. It takes 4 seconds to do it. That must be the whole 1,000 images. Ah, that's 1,000 images. So you must be thinking like 0.5. Okay, so we have a data set, ImageNet v2. I should probably throw the reference there. I'll probably add the reference sometime later. And we can get a picture of a goldfish, and we can run it through our local model. And we get the confidence of goldfish is 100%, which is great. So now what we're going to do is we're going to run through each index. So we're going to do 1,000 as kind of like a validation set for the FPGA. We're going to send the pictures over UDP, and we're going to get our results back over UDP. And we'll be able to run locally, and we're going to be able to run on the FPGA. And we're going to look at accuracy, and I should grab and after we'll talk about how we can get the value for the performance. Open up that file. Okay, so this is going to be fun. Back to where is it? Back to single terminal here. We're going to close that. Here. So we're going to reset the UI devices. This is for like some driver devices for interaction with the FPGA. We're going to grab the library for running the system and open up the reference. Okay. And then we're going to run the app. Oh, we didn't really talk about that. Okay. We also have a UDP version. This is on the GitHub. You can look at it. It's basically doing the same thing, except the images are being received from the host machine, and we are sending the results back as a string or as a struct back over to the local machine. Okay, so this is gonna be fun. We're gonna run through 1,000 images and see how long that takes. Okay, so we start this. Now it's waiting for us to run this. What? Goodness. But the IP was the same. Check this out real quick. Right? Like 225? 33? Yeah. It didn't even send the first one. That's weird. Could have got something. I'm gonna stop this. I love it when you test everything and you have a little hiccup. Huh. Okay, so we're going to run cells above. That's a sock. Yeah, that's what we're sending it on. And we set it up. Oh, yeah, the address. Here. Waiting to receive on that port. Yeah, weird. Okay, I guess we'll try again. There we go. I want the first hiccup was. Okay. So now we are sending the images from the machine to the FPGA and back. We're collecting accuracy for top 1 or top 5 indices. And we'll go through all the pictures. And bring this up for a little bit, be a little bit better. Deepak, it's you have a comment on YouTube chat about running OpenVINO in the lab on the Agilix 7. What type of difficulties did you have in setting up the Agilix 7? I do feel like there's sometimes, how do you say, when you're trying to do a new configuration, it's hard to figure out what the correct settings are. Were you using a default configuration, or did you have a custom configuration when setting up your Agilix 7? Okay, we're getting close. 900s. Okay. So we can look at the accuracy differences. So the local machine with the correct pre-processing, I brought that out as well. With the correct pre-processing, got a 70%. I guess we should divide this by 10. Since there's 1,000. Whatever. So we got 71% accuracy on the CPU and 53% accuracy of the FPGA. But we include the top 5 count. It's about 20 and 25% for the CPU and the FPGA. Bringing that together, we got about a 92%, which is actually pretty good. That's pretty good for the YOLOv8 classifier. And then the FPGA got a 78%. And these differences are only because of pre-processing. The CPU and the FPGA should be in the exact same convolutions with the exact same parameters. So depending upon how I change the performance. So let's go back here, and we can change the shift, right? Like if we did 10, 20, 20, 30. This is that red, or the red, green, blue shift. We'll have to reboot. We can see the differences there. While it's rebooting, we can look at the timing of each. Okay. I want to look at my test now for getting the timing. How do we get the time? Okay, it's going to be in the results. So we'll have to go look at the results summary. Okay. Code results. That's summary. Batch 0 results. Okay, we want to get the timing. Where's the timing located? Speed. Okay, we want to look at inference. So we want to do speed. We do dot speed and inference. Oh, is it? It's probably a function, so it wants something like that. Oh, no, it's a dictionary. Okay, there is our inference in milliseconds. Okay, so inference is 60. So if we process the image again. Oh, it's quiet now. It takes 11 milliseconds. Okay. I want to create, look at the average inference time. So local inference time. We want to do an array. And we're just going to do what? And results inference. It'll be in milliseconds. And then here we want to do FPGA inference time dot append. I think it's going to be just float 2 and divide that by 1,000. Is float 2 correct? Float 2 is the inference time. Okay, so that should be good. Okay, so we should be good to reboot now, and then we can run it with the phase shifting and measuring the inference time, and then we can look at the average inference time. Okay. Started. App on the stream. App. Python 3. YOLOv8. UDP variant. Okay. I think we're good. So we're going to capture the inference time as we go about this. We mess with the phase shift, so we should get different accuracy. Bring this over, and then we can look at the power. Oh. Guess we can scroll down. Okay. So we come to the top of the hour. We're probably just going to be going another 15 minutes. But if you joined us recently, thank you for joining. This is a Altera sponsored stream looking at using their FPGA AI suite on the Agilix 7 FPGA. I am FPGA Zealot. You can find me on YouTube, Twitch, and LinkedIn. Thank you for joining us. And if you have any questions about what's happening, feel free to use the chat in LinkedIn, Twitch, or YouTube. Okay. Whew. So we're going to expect the accuracy to be different as we played around with the face, the color shifting. So it's about the same. Let's see, did this change? That went up a little bit. And yeah, relatively the same. But let's look at our local inference times and the FPGA inference time. I think I'm supposed to do times 1,000. Let's update that real quick. I didn't do that correctly. And change that to the times. And now this should well, we'll just multiply it by the million when we get the average. So let's go ahead and get the average here. This is going to be the sum of this value divided by the length of the local inference time. So our average is 8.6 milliseconds. So the sum of the FPGA inference time divided by the length of the FPGA. I mean, it's going to be 1,000, but okay. And then we're going to times this by 1,000 and times by 1,000. That on the outside. Oh, sorry. It's supposed to be like that. Okay, so our FPGA was able to operate at 3 milliseconds on average for the inference time, while my multiprocessor is operating at 8. So the FPGA is using less power. I mean, honestly, probably less DDR requirements and whatnot, and still has a lot more fabric to utilize, and has a faster inference time. So this is how an FPGA is competitive with a multiprocessor CPU and also with a GPU, depending upon how you utilize that pre-processing, post-processing in an embedded platform, especially for edge computation. Uh, I That's going to be probably what we have for this year in FPGA AI. I really want to look at the Agilex 5 and large language models or small language models, and I think that would be an interesting thing to get running on an FPGA. So hopefully next year we'll have more opportunities to look at the AI suite and the Agilex 5 and be able to do some more interesting examples. I definitely gotten my feet wet, and I'm excited to try to explore some more complicated designs where we kind of utilize the FPGA for pre-processing and post-processing, because that's where the FPGA is going to shine, is where you're doing application-specific, custom pre-processing, post-processing of the neural network computations. So we got probably about 10 minutes before we'll stop the stream. So if you have any last minute questions or comments, feel free to ask them now. We can address them, have a small discussion, and then we'll end for today. But thank you for coming, and please leave a like, a subscribe, or whatever to show your interest in future live streams about FPGAs or about Agilex 7 or the Altera FPGA AI suite. I would love feedback to know what topics interest people the most. So the sixth Hokage has a question on YouTube. How much computation power does my FPGA need to run the model? So mattering which tools you use the example of an RTX 7 FPGA. So Altera's FPGA suite is for their FPGAs and uses their tool suite. While that FPGA target does have its own tool suite, it does not target that small of an FPGA. If you want to do an RTX 7 neural network, you basically will need to find a open source neural network implementer that for FPGAs, some type of HDL or whatever, or you'll have to write the convolutions from scratch. Depending upon how you do it, you'll probably need external DDR. So if you have an RTX 7 FPGA, you'll need external DDR, and you'll need to write the HDL to do the convolutions and to load the parameters from the DDR during operation. And it's a relatively big project. That's why FPGA AI Suite is such a useful tool, because you don't have to focus on implementing the convolutions, implementing the data management to bring the parameters from the DDR to the convolution. And unfortunately, I don't know of any good examples to run for that target FPGA. The Agilex 5 FPGA coming out next year, and the Agilex 3 after that, should hopefully fall better within the academic hobby community, that you'll be able to prototype these AI cores on those development boards. I want to rerun this one more time. So we're going to do that. Document. Inference. Python going. Python 3. YOLOv8. P. 1,000 there. Here as well. Okay. Let's run this one more time. Okay. I'm kind of excited. This is where we were able to end up on for these Altera sponsored live streams, that we were able to get to the point that we have YOLOv8, a kind of an official neural network that everyone uses, able to export that model to the FPGA and be able to run it with like this type of platform where we're sending and receiving images and be able to kind of compare those results. I'm really excited next time to kind of dig more into the FPGA fabric and be able to do some either modifications to the FPGA image, that we can do some unique pre-processing like a large language model tokenization process, or maybe try to figure out how to manage the bounding boxes on YOLO, the YOLO bounding boxes version, maybe push to YOLOv8, or try to look at other networks and maybe make to support my own model zoo for the Agilex FPGAs. Okay, so we've ran it through it again. We can see if the accuracy changed. It's about the same. And then we can look at the inference times. And yeah, the FPGA is about 3 times faster. Yeah, about 3 times faster than the multiprocessor CPU. Whew. Okay, so there's been 1 hour and 10 minutes of FPGA AI Suite and Agilex 7, and this has been sponsored by Terra. It's been great. If you want to follow for more videos, look for YouTube, X, Twitter, Twitch, or LinkedIn. And hopefully we'll see some more postings, maybe a video, another stream or two before the end of the year, but next year as well, looking at more FPGA and FPGA AI related applications. Thank you for joining. It's been great to be able to have this opportunity. I will stay on for a few more minutes in case anyone has some final questions, but I'll probably be closing the stream in a few minutes. But thank you. Ham radio operator, you're welcome. I'm glad you could join us on the Twitch side. Oh, I'm ready for a fun Thanksgiving weekend. Okay. See you guys next month or next year, whatever comes first.